Hello students, by now we know the concept of groups, periods and how to locate an element's position in the periodic table based on electronic configuration. Let us discuss few physical properties and their periodic trends. After this discussion, you will be able to explain and compare the different types of atomic radii, discuss the periodic trends in atomic radii, ionic radii and ionization enthalpy of elements. Explain the relationship between ionization enthalpy and metallic character. Use scientific vocabulary appropriately to communicate ideas related to certain important properties of atoms, example, atomic radii, ionic radii, and ionization enthalpy. By now, we know that the long form of periodic table is based upon the modern periodic law and the elements are arranged in the order of their increasing atomic number. There are 18 groups and 7 periods in the periodic table. There are many observable patterns in the physical and chemical properties of elements as we descend in a group or move across a period in the periodic table. But why do the properties of elements follow these trends? And how can we explain periodicity? The real meaning of word periodic in any classification of element is that when the elements are arranged in order of their increasing atomic numbers in the same period or group, there is gradual change in a particular property. In a period, the gradual change is due to gradual change of electronic configuration from member to member. In a group, the chemical properties remain nearly the same due to same valence shell configuration, but there is a gradual change in physical properties. This is due to gradual change in the size of atoms due to increase in energy shell as we move from top to bottom. Students, we shall now discuss the periodic trends in some of the properties. The first important physical property which we shall discuss is atomic radius. An atom is assumed to be spherical in shape and thus the size of atom is given in terms of radius of the sphere and is called atomic radius. It is usually defined as the distance from the center of the nucleus of the atom to the outermost shell of electrons. It is difficult to measure precisely the radius of the atom for two major reasons. First, atom is too small to be isolated and measured. Second, atom does not have a well-defined boundary because the probability of finding the electron is never zero, even at a very large distance from the nucleus. However, it is possible to calculate the radius of an atom from the distance of the atoms in the combined state. It is equal to 1/2 of the distance between the nuclei of two atoms bonded to each other. However, bond lengths change with different types of bonding. Three types of radii are commonly used. They are covalent radius, which is defined as half of the distance between two nuclei of two like atoms bonded together by a single covalent bond. Covalent radius is used for nonmetals. Metallic radius, which is half the internuclear distance separating the metal cores in metallic crystal. And van der Waals radius, which is half of the distance between the nuclei of two non-bonded neighboring atoms of two adjacent molecules in solid state. A comparison of three types of radius shows that covalent radius of an atom is shortest while van der Waals radius is the longest. For simplicity, we use the term atomic radius to refer to both covalent or metallic radius depending on whether the element is a non-metal or a metal. Do you know how the radius of an atom varies in a period and a group of the periodic table? Generally, atomic radius decreases across a period and increases as we go down a group. Let us try to find why. In a period, as we move left to right, the nuclear charge increases by 1 unit in each succeeding element while number of shells remain the same. As a result, the effective nuclear charge increases and the electrons in the valence shell gets more strongly attracted, thus making the atom smaller and smaller. Thus, we can now very well visualize that the largest element lie on the extreme left of the periodic table and the smaller ones are placed on the extreme right. Going by the trend, Noble gases being at the end of each period should be smallest in size. However, it has been found that their size are larger than halogens. This is because for noble gases, we take into account van der Waals radii as they do not form covalent bonds, and van der Waals radii are larger than the covalent radii. Let us now learn about the variation of atomic radii in a group. Atomic radius increases from top to bottom within a group. As we move down the group, the nuclear charge increases, but at the same time, there is progressive increase in the principal energy shells. The effect of additional energy shell is more pronounced than the effect of increased nuclear charge. Therefore, the effective nuclear charge decreases. Thus, the distance of the outermost electron from the nucleus increases on going down the group. Now let us learn about the variation of second property, that is ionic radius. How are ions formed? Yes, a positive ion, that is cations, are formed when a neutral atom loses one or more electrons, while negative ions, that is anions, are formed when a neutral atom gains one or more electrons. The effective size of these ions are termed as ionic radius. Ionic radius may be defined as the effective distance from the center of the nucleus of the ion up to which it exerts its influence on its electronic cloud. When an atom loses or gains an electron, its size changes. Do you know? A cation is always smaller than its present atom, whereas an anion is always larger than its parent atom. Let us try to understand the reason. Formation of cation involves loss of electrons. The nuclear charge remains the same as the parent atom, but the number of electrons decreases. As a result, the remaining electrons experience greater force of attraction. This causes decrease in size. On the other hand, formation of an ion involves gain of electrons. An increase in electron results in decrease of effective nuclear charge per electron and thus resulting in an increase in the size. Ionic radii, just like atomic radii, follows the same trend across a period and down the group. That is, decreases across a period and increases down the group. Do you know? There are certain ions which have same number of electrons. The ions and the atoms which have the same number of electrons but differ in the magnitude of nuclear charge are called isoelectronic species. Example, nitride ions, oxide ions, fluoride ions, sodium ions, magnesium ions, and aluminium ions. They all have 10 electrons in them. Do you think that isoelectronic species have same size as well? The answer is no. In the series of isoelectronic species, as the nuclear charge increases, the force of attraction by the nucleus on the electron also increases. As a result, the size of the ion decreases. The cation with the greater positive charge will have a smaller radius because of the greater attraction of the electrons to the nucleus. An ion with the greater negative charge will have the larger radius. So it is evident that the order of size in series taken earlier is nitride ions greater than oxide ions, greater than fluoride ions, greater than sodium ions, which is greater than magnesium and aluminium ions. We know that cations are formed by loss of electron. Students, do you think there is any energy change involved in this process? Yes, energy is required to remove an electron from an atom. Related to this, we are going to learn about an important property of an atom, that is ionization enthalpy. It is a well-known fact that electrons in an atom are attracted by the positively charged nucleus. Thus, to overcome this force of attraction, energy will be required. Thus, the energy required to remove the most loosely bonded electron from an isolated gaseous atom in the ground state is known as ionization enthalpy. It is denoted by delta IH and is expressed in kilojoules per mole. The energy required to remove the first, second and third successive electron from an atom is called as first, second and third ionization enthalpy respectively. Look at the successive ionization enthalpies of aluminium. The second ionization enthalpy is always greater than the first, and the third ionization enthalpy is greater than the second. Student, why is it so? Let us try to understand why. On removing an electron, the effective nuclear charge per electron increases, and hence the remaining electrons will be held more tightly by the nucleus. Thus, more energy is required to remove the second electron. For the same reason, the third ionization enthalpy is larger than the second. Do you know how ionization enthalpy changes in a period and a group of a periodic table? Ionization enthalpy generally increases across the period. As we move left to right in a period, nuclear charge increases regularly. Thus, the outermost electrons are held more tightly, resulting in the increase in ionization enthalpy. However, there are few exceptions. Beryllium has configuration 1s2, 2s2, whereas boron's configuration is 1s2, 2s2, 2p1. In beryllium, the 2s orbital is completely filled, and moreover, the electrons are present in the more penetrating s orbital. On the other hand, in boron, the outermost electron is present in the less penetrating p orbital, and hence less energy is required to remove an electron from the 2p orbital of boron than 2s orbital of beryllium. Another exception is the smaller ionization enthalpy of oxygen as compared to nitrogen. Again, we can understand the reason by examining the electronic configuration of both these elements. Nitrogen has configuration 1s2, 2s2, 2p3, whereas oxygen has configuration 1s2, 2s2, 2p4. Can you try thinking of the reason for this anomaly now? Yes, it is due to the half-filled 2p orbital in nitrogen. Due to the stable configuration, nitrogen has less tendency to lose an electron, and hence more energy is required. Students, can you figure out more anomalies in the periodic table? Now let us learn about the variation of ionization enthalpy in a group. The first ionization enthalpy of elements generally decreases as we move down in a group. To understand it better, let's have a look at the values of ionization enthalpy of group 1 elements. Ionization enthalpy increases from lithium to cesium. As we go down a group, although the nuclear charge increases, ionization enthalpy decreases down the group. This is because the effect of increasing nuclear charge of electron in an atom will be less than the actual charge on the nucleus due to shielding or screening of the valence electrons from the nucleus by the intervening core electrons. Due to this, the nuclear attraction on the outer electron decreases. Thus, it becomes easier to remove the electron. Hence, ionization enthalpy decreases down the group. Students, so now we can visualize that elements which lie on left side of the periodic table have high tendency to lose electrons. Students, from the discussion till now, we conclude that atomic radius of an atom is the distance from the center of the nucleus to the outermost shell containing electron. Atomic radius decreases across a period and increases down the group of the periodic table. Ionic radius is the effective distance from the center of the nucleus of the ion up to which it exerts its influence on its electronic cloud. The radius of cation is always smaller than that of its parent atom, while the radius of an anion is always larger than its parent atom. Ionization enthalpy of elements is the amount of energy that an isolated gaseous atom requires to lose an electron in its ground state. As we move from left to right across a period, ionization energy of elements increase, and as we move down a group, ionization enthalpy of elements decrease. Students, here are a few questions for you to practice. Question 1. Out of the following ions, which has smallest ionic size? Lithium ions, sodium ions, or potassium ions? Question 2. Arrange each of the following sets of elements in the increasing order of their ionization enthalpies. First, oxygen, nitrogen, sulfur. Second, lithium, beryllium, sodium. Third, neon, helium, argon. Question 3. Out of sodium having atomic number 11 and magnesium having atomic number 12, which has higher second ionization enthalpy and why? Can you relate the atomic radii and ionization enthalpy with chemical reactivity? Students, I'm leaving you with this food for thought. Have a nice day. Thank you.